Welcome back to the deep dive. So, today we're going to tackle something, well, something huge. Magnetism.
It really is. And our source material for this is just fantastic. J.H. Van Vleck's 1977 Nobel Lecture.
And the central mission here, the puzzle we're trying to solve, is pretty stark. People have known about magnets for thousands of years.
Right, lodestones, compasses. But the actual why are some things magnetic? That question completely stumped the greatest mind until quantum mechanics came along.
So this is really a story of failure. First, the total failure of classical physics to explain something we see every day.
Exactly. We're talking about the late 19th, early 20th century. Ørsted, Ampere, Maxwell, they'd done this incredible work linking electricity and magnetism.
The foundation was there. They knew it had to come from moving charges, electrons orbiting an atom or something.
But every time they tried to build a model using classical rules, the math just fell apart. It told them magnetism shouldn't even exist.
Okay, so let's get into those big classical attempts. The first one was for ferromagnetism, right? The weak stuff.
Yeah, weak attraction. Think liquid oxygen. In 1905, Paul Langevin comes up with this really elegant model.
And his idea was that every atom is like a tiny compass needle, a magnetic moment.
A tiny compass needle, exactly. And an external field tries to line them all up. But the problem is heat.
Thermal energy. It just jiggles everything around, messing up the alignment.
Right. So Langevin uses the Boltzmann factor, which is basically a way to calculate how much that thermal chaos fights against the magnetic alignment.
And it worked amazingly well.
It worked perfectly.
Yeah.
Under normal conditions, his equation simplified down to Curie's law.
Which had been seen in experiments a decade earlier. Magnetic strength is basically 1 over temperature.
Yep. The hotter it gets, the weaker the magnet. It looked like a huge victory for classical physics.
But it was built on, let's say, shaky ground.
Very shaky. And the next problem was even bigger. Ferromagnetism. Iron. The really strong stuff.
This is where Weiss comes in 1907.
And he has to explain why iron atoms all line up spontaneously, without any external field at all. To do that, he had to, well, invent something.
In the mysterious internal or molecular field.
That's the one. He just proposed that there was this incredibly powerful internal field that forced all the atomic magnets to align.
So wait, he just made up a field nobody could see or measure? Why did people go along with that?
Because it worked. Qualitatively, I mean. It predicted the Curie point, the temperature where a magnet dies. It described the behavior beautifully.
But the numbers didn't add up.
Not even close. To get the high Curie temperatures you see in real materials, that internal field had to be like 1,000 times stronger than anything classical physics could possibly explain.
An impossible force. So one theory for weak magnets works but has hidden flaws, and the other for strong magnets works but needs impossible physics. That's not a good situation.
It's a crisis. And then comes the final devastating blow from Niels Bohr, of all people.
This was in his PhD thesis, right? 1911.
Yep. And Van Vleck calls it perhaps the most deflationary publication of all time.
What did he prove?
He proved rigorously that if you use the rules of classical physics, statistical mechanics, all of it, the paramagnetic and diamagnetic effects must cancel out perfectly.
So if classical physics were 100% correct...
there would be no magnetism at all. The universe would be non-magnetic.
Wow. The very existence of a refrigerator magnet proves that all of classical physics is fundamentally wrong at the atomic scale.
That's it. That's the paradox that breaks everything.
And that forces the transition into the quantum age. So the first attempt at a fix was what they call the old quantum theory.
Right. This is around 1913, Bohr's idea of quantization, that things like angular momentum can only have specific, discrete values, not just any value.
And the Stern-Gerlach experiments proved this in a really dramatic way.
Oh, absolutely. They shot atoms through a magnetic field expecting a smear.
Like a spray paint pattern.
Yeah, but instead, the beam split into a few sharp, distinct lines. It proved that the magnetic moments were locked into specific orientations. They were quantized.
So going back to Langevin's model from 1905, it only worked because he was accidentally doing something quantum without knowing it.
He was, as the source says, unknowingly quantizing the system. But this old quantum theory was still a mess. It only really worked for hydrogen.
And that led to, what, a decade of disillusion and disappointment?
Pretty much, until the Big Bang of 1926-28, a miraculous few years.
This is when it all comes together. You get wave mechanics from Schrödinger, matrix mechanics from Heisenberg.
And the last crucial piece of the puzzle, electron spin, from Uhlenbeck and Goudsmit.
which Dirac then synthesizes into the general theory of quantum mechanics.
And he's so confident he says the underlying physical laws are now completely known. And one of the first things this new theory does is go back and fix magnetism.
It fixed that statistical problem in the Langevin model.
Immediately. It restored a numerical factor, a factor of 1/3 that just pops out of the math naturally. It brought order to the chaos.
Okay, so now they have the tools. This is where they go from just fixing old problems to actually making new predictions, right?
Exactly. And one of the first big tests was the nitric oxide molecule, NO.
Why was NO so special?
Because it just didn't follow the simple Curie law. Its behavior was weird. So in 1927, Van Vleck takes the new quantum mechanics, applies it to the energy levels of the molecule.
It makes a bold prediction.
A very bold one. He predicted that its magnetic character would change, and change significantly with temperature. It wouldn't follow that simple 1/T rule at all.
That's a claim you can really test.
And they did. Within 2 years, labs all over the world confirmed it. The data matched the quantum predictions perfectly. It was a huge triumph.
And this leads to a general formula for magnetic susceptibility. This is where it gets really interesting, because it's not just about the basic energy level.
No, this is the key insight. To get it right, you have to know the atom's energy states up to the second order in the magnetic field.
Second order Zeeman effect. So the field is kind of mixing energy levels together.
A little bit, yeah. And the behavior you see all comes down to one comparison: the spacing of those internal energy levels versus the thermal energy, KT.
And that was the key to solving the big anomaly with the rare earth elements.
Oh, the famous case of samarium and europium. Yes.
Hund's rules had worked for almost all of them, but failed completely for those two.
Because for Sun and Dew, the energy gap to the next highest magnetic level is really small, comparable to KT. Everyone else had just been ignoring that second-order term because for other elements, the gap is huge.
So the error was in the approximation, not the fundamental rules.
Exactly.
Yeah.
Van Vleck and Frank went back in 1929, put that second-order correction in, and the theory just snapped right into place with the experimental data. It was a beautiful confirmation.
So from there, the theory moves on to ions inside solid crystals, crystal field theory.
Right. How does the local environment, the neighboring atoms, change things? And the key concept that comes out of this is quenching.
Quenching the orbital momentum.
Yeah. The electric field from the surrounding crystal lattice can effectively lock the electron's orbital motion in place. It stops contributing to the magnetism as much.
And the spin is mostly left alone.
Usually. And this whole idea leads to what Van Vleck called his favorite paper. It solved a really tricky puzzle with nickel and cobalt salts.
What was the puzzle?
Well, nickel salts were magnetically simple, isotropic. Cobalt salts were wildly anisotropic. Their magnetism depended heavily on direction. The only way to explain it seemed to be to arbitrarily flip a sign in a constant when going from nickel to cobalt.
Which sounds like cheating.
It felt like cheating. But Van Vleck showed it wasn't arbitrary at all. He proved that a deep mathematical symmetry principle, the invariance of the trace for the technically minded, forces the energy level pattern to invert between nickel and cobalt.
So what looked like a cheap fudge factor was actually a profound requirement of quantum mechanics itself.
Yes, it brought consistency and rationality to what seemed like a total mess. And that idea is now the foundation of modern ligand field theory, which explains everything from why blood changes color to high spin and low spin chemical states.
So when you step back and look at the whole arc, I mean, from the complete dead end of Bohr's proof to these incredibly precise quantum solutions.
It really is the story of 20th century physics finding its feet. A 50-year journey from total confusion to quantitative mastery.
And that foundation just kept paying off. It led Heisenberg to finally explain that mysterious Weiss field.
He explained it as a quantum exchange effect, a totally non-classical force, and it led to understanding electron spin in metals and eventually to things like nuclear magnetic resonance, NMR.
Which is an indispensable tool today. It's just incredible how that one master key, as the source calls it, keeps unlocking more and more doors. We saw it explain the nickel-cobalt difference, and then years later, the same math explains weird magnetic effects in exotic alloys.
It absolutely does. The framework is just that powerful. But of course, the story doesn't end there.
Right. And that brings us to our final thought. And we keep finding these new, incredibly complex magnetic states of matter, things like helical magnetism, spiral magnetism, especially in rare earth metals.
Really strange, beautiful structures.
So if quantum mechanics truly is the master key, how might the continued discovery of this kind of Weird magnetism. Keep pushing and maybe even extending the boundaries of that powerful quantum framework. What new doors might it force us to unlock?